Bro, why are you sucking on a USB?
I'll be in the video now. We're doing current electricity, direct current mostly in this class, but we will talk about alternating current, but that's going to be more in the electromagnetic section. Okay. So simple circuit.
Doesn't that mean lights?
That's a coil of some kind, right?
Really? I didn't know that.
So this is a bulb.
And that's the switch.
This is a cell.
Oh, never mind.
So what is a cell?
Battery. Car battery.
Yeah, it's kind of a battery. Technically, one of these is a cell, and if we go like this, if we put two cells in a row, then that is a battery.
Why only if there's two?
Because a battery implies that there's more than one cell. I told some other class, but the term battery was made up by Ben Franklin. And he had these Leyden jars that are like, you put an ionize like a salt water or something like that, and you can store charge in them. And then if you link them up together, you get a big charge, and so he called that a battery. Originally from cannons on ships, because you batter your enemy. Okay, if we want to put a switch in here, well, let me start with. We're going to do a lab soon, and I will show you this, but you have the way that I explain this, I'm going to explain this in the grade 9, 10 version first, okay? So I'm going to take some liberties here, but this side of the cell pushes electrons out. We don't call that current. We call current going out the positive side. Current. Okay. What is current? Hello, sir. You know current.
Yeah.
You understand.
How are you?
Good.
Josh Kim?
Yes.
Oh, do we have awards?
Well, they were not here last time I visited.
Oh.
Congratulations for achieving honors with distinction.
Yay!
Honors with distinction last year. Congratulations.
Yay!
Dana? Honors
Hello.
with distinction.
Yay!
Congratulations.
Why are we clapping? This is not even a class. You automatically get it.
You automatically got one.
Participation awards.
Thank you.
We can change that.
Yeah.
Just send me a
Yeah.
list of names.
Yes, that's
Thank
right.
you.
Thank you, Mr.
Have a
L.
great day.
You too.
I'm a 4-time.
Victor.
I'm a fuck.
Is the plus always at the right side and the negative?
Yeah, the long side is positive and the short side is negative. That's not like super important, but. So current comes out of the positive side. Even though we know that it's the electrons that move, but as Sherry pointed out in my last class, so we're not even sure the electrons move, so we'll just keep that on the down low until we learn quantum. But for now, we're doing the grade 9 way because I think it's good to have a really kind of basic fundamental understanding before we tell you it's all a lie and ruin everything. So the battery pushes electrons out this way. It's actually in the opposite direction of current. Everything that we do in electricity is based on a positive test charge. So you know how the electric field lines went away from positive charges and into negative charges? That's because the electric field is based on a 1 Coulomb positive test charge. And so that's what a positive charge would do, right? So if you have
Like if there was a negative one, it would pull it in. If there was a positive one, it would push it out.
yeah, so if you have a positive and negative, your field lines would, are based on what a positive charge would do. If you put a positive charge right here, where will it go?
Go
Point.
towards.
Yeah, it's gonna get pushed away and pulled in, right? So your field is going that way.
Oh.
And like this, right? And like that.
Sorry, the
So
middle
it's
line
all-
isn't really clear. How is it
Just
just
a straight
straight
line.
towards the negative? It's being pulled.
Yeah, if it's from positive, comes out of positive and straight towards negative. Is it hard to see?
No.
If it's out here, it'll get pulled in, right? So anywhere along this line is where a positive test charge would be pulled. It's the same thing with current. It's where a positive charge would go. So a positive charge would be pulled around this way. Even though we know that it's the electrons that actually do the moving, and they get pushed around the opposite way.
Yep.
Okay. So think of if you want a kind of way to simply understand current electricity, imagine your electron as a dump truck or a submarine. Which one would you rather?
Dump truck.
It has to be something that can. It has to be something that can carry stuff. Okay.
Dump truck.
What? Penise is shaking her head. What's wrong with the dump truck? I don't understand.
You have to.
Is he fixated on the word dump? Is that?
No.
No, it's a
It's-
dumpy. You should put that on the board.
It's kind. Oh, I hate
But-
explaining things to adults.
Let's be
It's when you
mature.
see, Mr. Osman, it's when you see a gluteus maximus of remarkable.
Do you know what you're talking
It's just a very crude.
Okay. Well, let's not talk about it. Let's be a little bit more mature. We have a truck here, okay, and the truck.
That's so funny, guys.
The truck has.
Thank you, Josh.
The truck has energy in it. Okay. This is energy inside the truck. The truck is the electron. Okay. And the electron's being pushed around. And the cell is what's pushing the electron. Now, it comes out, if this is a, let's say this is 3 volts. Okay. If this is 3 volts, that's, what is a volt?
It is a joule per coulomb.
Very good, Zane. It is a joule per coulomb. So if it's 3 volts, it's 3 joules per coulomb. So actually, maybe let's not think of our truck as 1 electron. Let's say there's lots of little electrons in here. And let's say this truck is 1 coulomb of charge. Okay. Do you know how many electrons are in 1 coulomb?
It's 1.6. It's a lot. If you divide it.
2.
No.
The charge on an electron is what?
1.6 times 10 to the negative 19.
So if I put in 1.6 times 10 to the negative 19, and then I inverse
And
that,
you divide it.
oops,
You have to divide it, which will give you the number.
yeah, so 1 divided by
By
that
1.6.
number is 6.25 times 10 to the 18. Okay, and so we say 1 coulomb, I'll write that out just to be clear, equals 6.25 times 10 to the 18 electrons. It'll become clear why we use this in a second here, but just bear with me. So let's say this truck is a coulomb. This coulomb carries how much energy when it comes out of the cell?
1 volt?
No.
3 volts.
3 volts.
Oh.
So if it's 3 volts and the truck is 1 coulomb of electrons, how much energy is in the truck? Good here?
3 joules per
3 joules. This is 1 coulomb, and we have 3 joules per coulomb
okay.
from our cell. So this is going to be 3 joules of energy. Does that make sense?
Yeah.
Wait,
Yes, Victor?
it's 1 coulomb. What is it? So it's still transporting the whole current, so 3 volts.
Yes. Yeah. So every coulomb, there's more than 1 truck here, right? There's a truck down here, and it's full of energy. And there's a truck over here, and it's coming down.
It doesn't
all one truck.
This truck
doesn't have
has very little energy,
Yeah.
right? Just
Just enough.
enough to get it home.
Yeah.
Okay, the truck coming back to the cell,
What happens if it doesn't have enough to get home?
it always does,
Oof.
and it always has just enough.
So just enough to get to like 0 and then it gets turned up.
Yeah, it's like my friend Brad in high school. He had just enough gas to get you there, and you could never get back. Yeah. He would
That's
put
kinda
in
how
just
I-
enough gas to get us to where we were going.
How does he bring the truck back?
Then we begged, borrowed, and other things. And we got ourselves home somehow. But we got there. And that's what the electron is like. It has just enough to get it to supply whatever energy it needs to supply, and then it will come back with absolutely zero. Just as it hits here. So it's using energy as it goes through the wire, but not very much. Wire is nice, smooth ride, it's open space. And then you hit this. This is a light bulb, by the way. Bulb. And as I go through there, I'm losing energy. What's happening to that energy?
It's transforming into like
Heat.
light and heat.
Yeah, you're losing it as
So
Light and heat.
light and heat. Okay. And so you'll go through there, and if you put two bulbs in a row, the electrons are very handy this way. They know I'll just drop half my energy at this bulb, and then I'll drop
How do they
half my
know?
energy at the next bulb.
How come they know?
They're very smart. They're IB students.
So
Wait,
that's
so does the bulb get dimmer then?
Yes.
yeah.
If you put two bulbs in series, you'll have half the energy drop.
That's so stupid.
And if you put 10 bulbs in series, you're only going to get a tenth of the juice.
That's
How
about-
how does it know?
Is there any bulb that like doesn't emit heat?
Well, LED bulbs emit less heat. That's why they're a lot more efficient.
So you can
They still do some though. Yeah. We don't know any bulb that emits no heat.
Would that be like a revolution if it emitted no heat?
Yeah. The LED bulb was a great revolution. I have the book about it actually.
And they're less expensive.
Is
Yeah.
it here? Oh yeah. By the way, these books are for you to read. They're all good. This book is called Brilliant. It's about this guy Shuji Nakamura.
Oh, I know.
You know him?
Yeah, I've heard of it.
He's my
Yeah.
favorite.
Not, I don't know him. I've
No,
heard of
my
him.
But you've heard of him.
Who's what's the name?
Shuji Nakamura is not a super well-known guy. He is the guy who he didn't invent the LED bulb, but he's the guy. He's the reason that we have LED bulbs in our home. He's this. It's a good story actually. He worked for this small light bulb company in Japan, and they were making like little doodads and stuff. And he was like, I wanna make the LED bulb a thing. And he went to his boss and he was like, I wanna make the LED bulb a thing. And his boss was like, fine. And he's like, I need $1 million. And his boss was like, no. And then he came back to him the next year and he's like, I wanna make the LED, and he's like, fine. And he gave him the $1 million. And they bought this big truck trailer machine that built LED surfaces, little silicon wafers. Same machine you would use to build a solar panel and stuff like that, transistors and things. And there were a lot of explosions. He worked all by himself, just him, and everyone thought he was crazy, and he was wasting all the company's money, and everybody hated him. And every like few days, you'd hear this boom, and he would come out of there and be all city faced and everything, and they're like, oh, he didn't die. And then one day he realized he knew a lot of chemistry and he knew a lot of physics, and he realized that the surface that everyone was using was the wrong elements. And he used gallium nitride, and that was the combination that ended up working. And so he got it working, And his boss was like, well, that's pretty cool. He actually did something. And he went to this conference in California. And everybody there from all the different universities were coming and they were showing off their LED light bulbs. And it was the auditorium and they were like, we've been working on this for 4 years at Princeton and like, we gotta shut off the auditorium lights and they like shut the lights down. And they was like, here's our bulb. And they flick it on, it's like, and you can like barely see it, right? And everyone's like, oh my gosh, they made light out of it, like, yay, right? And then Shuji gets up there and he's like, yeah, I made one. He's like, and it's like, boom. And everyone's like, what? He made it bright. Like, how did he do it? You know? And
Why didn't you patent it?
and it was just, oh, he did.
Oh.
He did. And he was the first one that actually made one that was like brightly lit. And then the next year, all these university people were like, oh my gosh, we got observer. What did he do and how did he do it? And then they came back the next year and like, yeah, we all did it. We all did it. We all made a bright bulb. And he's like, I got a red one. And they're like, wow, you know. And so this guy was like, for 6-7 years, he was a step ahead of everybody. And he made super bright bulbs, and he made all the different colors and everything. And he made his company, you know, billions of dollars. And so, of course, in the end, they fired him. And he's now a prof at UCLA, I want to say. Maybe UC Berkeley, something like that.
Why did he
I
get
think-
fired?
You know, Victor, these things just, they happen. They happen.
No reason.
You got to read the book. It's an interesting story. It's an interesting story about physics, but it's also an interesting story about business and the education world and the patent
What's his
world
name?
and the world of invention
I
and all
don't
that
like.
stuff. Shuji Nakamura
How do you spell
is his
that?
name. The book is called Brilliant. It's really good. That was a complete and total aside. Sorry, I don't know about that, but interesting story. The bulb makes light and heat. A more efficient bulb, like an LED, will make less heat, more light, right? So you can use a smaller voltage cell and produce more light, right? Okay, so the current is the electrons going around, right? Except we say it's the opposite direction.
See, UC Santa Barbara? Who would choose to go there?
UC Santa Barbara, that's a nice spot.
They live in California.
Santa Barbara.
What is the unit of current?
Ampere.
Amperes. So 1 amp of current is, I'm gonna erase this here. Say that again, Karosh. It is 1 coulomb per second.
Time.
So, if you got on the magic school bus and you shrunk down and you went inside the wire and we watched these Coulomb trucks going by, if you counted 5 trucks going by in 1 second, what would the current be?
5 amps.
5 amps.
5.
If you counted 10 coulombs in 5 seconds, what would be the current? 2 amps, right? So that's all current is. It's just the number of charges going by in a given time. If I take this bulb out, no light and heat, no bulb, and I just connect the wires, I just say,
Well, I can't do that in my drawing.
okay, then do this, then do this. Here's my bulb, just go like this.
Okay.
If I hook that up, so in other words, if there's a short, what happens to the current?
It will.
Do you think there'll be more current or less current?
More.
Arvin, what do you think?
It's like the light, the bulb isn't there anymore, so you're not using.
It will run out of energy slower.
You have more.
It will run out of energy slower.
So you can push more electrons through.
Yes.
Think of it if you're driving, if I tell you, you gotta get in your car and you gotta drive over Landscape Bridge through downtown, come back over Second Narrows and come back to here.
Or you can just.
Downtown is a mess, right? So you're driving through, trying to go. And then somebody says, hey, We got it. We made a brand new road. Right? It goes around downtown, and it's open. There's no traffic on it.
Just,
Are any of you gonna drive downtown?
Yes.
It depends.
Yeah, but only John.
Beautiful.
Right? Sorry, he's riding the Tesla. One of you might drive downtown, but the rest of you are gonna take the open road, right?
They all take the open road, that becomes busy, I drive downtown, I'm a genius.
So you're gonna go fast through here. It's an open road, so the resistance is down. So resistance is like traffic. It's the way that you can think of it. So if you have a nice big open highway, you can have a lot of traffic, right? So that's low resistance. If you have a tight 1-lane gravel road and it's bumpy, that's a high resistance. Does that make sense?
Yes.
yeah, because you can fit less in the gravel and
Yeah.
more.
You're gonna have less. And of course, if you have more than one pathway, like if I go like this and I have another pathway,
All of them will end up with low.
that's gonna lower the resistance because anytime the traffic has more roads to go through, that's lowering the resistance. You get a higher current. Okay. In practical terms, the voltage is dependent on the cell. Okay. Resistance is R, and it's measured in ohms. And it's symbolized by the Greek letter omega.
Isn't that what?
Yes, ohm. How do you do the? Oh, that's nice.
What's the other one? What's the one in
If we
circular
don't
motion?
figure
It's
Now
like,
you
This
Touch your thumb to your
get
middle
on one
finger.
leg. Get on one leg.
That. You can do that. And so the law. Get rid of this.
Omega.
It's ohm Coulomb square per joule per second.
Say that one more time.
And it's ohm equal to Coulomb square per joule per second.
Yeah,
Yeah.
I think so. R is equal to V over I.
Oh wait, oh yeah, right.
You could also say V equals I R.
Or R.
This is Ohm's law. It's back there somewhere in the blue. I is current. Thank you for saying that. So V is volts in joules, so that's joules per coulomb. Can they see this in the video? Here, I'll just.
Oh yeah, a little, they can't see like the R, but they can see the I.
I'm gonna do a lab with you, a quick informal lab, and you'll see this. You can prove this to yourself with our power sources and our meters that we have. We have some nice brand new meters, and you'll prove this V over I by measuring with different resistances. You'll change your voltage on your power supply and measure the resulting current, and you'll find that when you do that with a given resistor, it goes like this. I'm giving it away, but I feel like that's okay. And the slope of this will be what?
R.
The resistance of your, whatever resistor you're using. A bulb can be thought of as a resistor. So we might draw it like,
Because it hinders the path of electrons.
yes, the resistor hinders the path of electrons, that's right. So this is a resistor. And you might say this was a 100 ohm resistor, or you might say it was a 10,000 ohm resistor, or you might say it was a 4 milli ohm resistor.
Like 1 mil.
So
4 million.
what is I?
Would,
Thank you for asking
would
that.
electrons even be a current? It's current, right?
So V is volts, I
It's correct.
is current.
So what stays constant though?
Yeah. in
Is
amps.
that the current or is it?
Well, I feel like all of them would be,
In a circuit like this,
would be
the resistor is baked into the, the resistor is baked into the actual mechanical thing. So it's like a road, right? The road's not changing
well,
in most cases. And this is the pressure. So this is the voltage, right? So maybe your R equals 2 ohms and maybe your voltage equals 5 volts, let's say, right?
And then you can find
So what's your current going to be?
2.5.
Yeah, 2.5, right? Because your R is going to equal V over I, and so you got 5 over 2. And so the current in this will be equal to 5 over 2. And so that's, why don't we just say that to be clear, 5 over 2. And what would be the unit of this? Amps. 5 over 2 amps. Of course, it's not going to be that simple, right? And we can add a bunch of resistors in both series and parallel, and I'll show you how it gets really complicated. But this is the general gist of what happens. This, with a power supply, we can change.
with the,
And you can have a variable resistor as well. Does anybody have a stereo at home where you turn the dial? And it goes, that's
you
more
can,
mine.
that's changing the,
Yeah, so a variable resistor looks like this. What actually happens mechanically is they take this, if it's a coil, and you wrap it in a circle. And you have this little connector. So if this connector comes out to the end, this connector can move up and down the resistor. If it's at the end, what's the resistance? Nothing, very
Really?
small. Because the electrons will go in here and go around the whole resistor and go back into the wire. But what if this conductor is up here at the front?
It's maximum resistance.
Then there's no way around the resistor, so you have a maximum of 2 ohms. If it's in the middle, it's going to be 1 ohm. And so you can turn your dial of your volume, and the higher, the more resistance means a lower volume, and the higher,
Could we
the
apply
lower
this?
the resistance, the higher the volume.
Could we apply this to? This might sound stupid. Could we apply this to our cathode ray tube?
Yeah, you totally can. And that's essentially what you were doing when you're turning up the power and down
So
of your power supply.
What's that turning up of the voltage?
Yeah, it's exactly this. So
So you're
with
moving
in the
it through
power
the coil?
supply, you have a power supply of 30 volts constant,
Yeah.
and you vary the resistance that it has to fight through.
Oh, and that was the.
That was in the-
Yeah. It's probably a little bit more complicated than that, and that actual thing, but
Yeah.
that's the gist of it. Okay. We should do a few little problems, I guess, eh? How much time do we have?
Like 7 minutes.
Okay. Let's just do a couple little things, just so that you can see how the math works. Yeah, sure. Give me a voltage.
30.
10?
30.
Let's say we got 10 volts.
Okay.
And we have a resistor with 50 ohms. And this is 30 ohms. And you have one more resistor. And hold on a second. And the current here. So if I want to measure the current, I'm going to put this in. This is an ammeter, which measures current, which you will learn how to use. make sure this number works. So if it's, let's say that this measures 0.1 amps. So there's 0.1 amps right here, and the question is, what is the resistance of this resistor? Discuss, think, and see if you can figure out how to do that.
Over I. R equals V over I. V is equal to. And what did we say? What's the other one? So we have 10 volts here, 10 is equal to 50 here. So this is 5.
But not the single one.
6.
Yeah, so 20. Because it's 100 and then minus 80.
So the first thing you have to realize is something about the current around a circuit. The current is 0.1 amps here. Where else is it 0.1 amps? Victor just went like this, yeah.
It's everywhere.
The whole thing, right?
Yeah.
How do you know it's 0.1 amps everywhere?
Because it is. It's
That's
connected.
what it is.
Because there's no branches here. There's no different pathways. So if there's 0.1 trucks per second here, there has to be 0.1 trucks per second down here.
Yeah.
There's nowhere for it to change. The current has to be the same all the way around. Okay, so that's an important concept here. The only way I can change the current is if I were to do something like this. Then I would have, okay, some of the trucks have to go this way and some of them have to go that way. But we won't worry about that right now. So the current's the same all the way around. And Joshua hit this right away. He was like R equals V over I. And so what's the V? 10.
Divided by 0.
And so 10 divided by 0.1 is equal to 100, right?
Yeah.
That's 100 what?
100 amps.
100 ohms is my resistance. But that's not for just this one resistor, right? It's for the whole thing. And so we have to have a total of 100 ohms in the whole circuit.
So there's 20 ohms down there.
Yeah, so this one has to be 20. So that I have a total of 100 ohms. In truth, it would be just a smidge less because you have to have a little bit of resistance in the wires. But we say that's negligible, we don't worry about that. Yes, Victor?
Can the resistance be negative?
Can it add more?
No.
Can it add more electrodes? Wouldn't it mean if the resistance was negative, it would be able to?
You can't go slower than stopped.
Yeah.
Okay.
Yeah. I guess go backwards.
I've tried that before.
Can you make electrons go backwards, back at the other electron?
Yeah, you can have back EMF, it's called, but that's not because of resistance, that's because of an a magnetic field that's pushing it back. We'll learn about that more
Electrons hit
later.
Each other and just like keep.
Pardon me?
But what if electrons just keep like going back at each other, just hitting each other?
Eventually, the one will win.
What?
It's kind of like if you have two buckets that are connected with a pipe, and they're full of water. And let's say that this one is here and this one is here. They're both pushing on each other, but what's going to happen? Yeah, they're gonna eventually equilibrate, right?
Yeah.
And so you're gonna end up at the same level.
So
That's
they
what
won't
it's like with
explode?
current. You can push one way and you can push the other way, and we'll do that. I'll give you circles of. Eventually, I will give you circuits with one battery pushing this way and the other battery pushing some other way, and there'll be branches and all that kind of stuff. And so you have to do that
So it
mathematically.
won't explode and kill everything?
No,
That's boring.
No? Sometimes it does get hot and melt things, but.
Boring.
Yeah, you have to. This is
You wanna explode stuff?
Yeah, like I said, dangerous equals.
I exploded something. Well, I'm gonna turn the video off here.
Good.
That's the basics. That's the first